for today, I'll be talking about this recent work I have with Daniel Pon and Yonggang from MPI. The title of the talk is really like a neo-gritty approach towards max-flow approximations. But I put a little asterisk in there because this is a work in a pipeline. We haven't really settled on the title of the paper yet. So if at any point you want to look up the paper, it might not appear with this name. Okay, so let me first tell you what's going to happen in this talk. So this result is really a new algorithm. I like to think as this algorithm in a model-independent way. It doesn't restrict itself to any particular model, and it works for like computing min ST cut or like more precisely the additive approximation max flow. The catch is that these algorithms I'm going to tell you is likely to be very poor in these sequential time models that we are all used to. It's likely going to be exponential time. But then if I look at two particular computation models, which are the communication complexity and the Kakuri model, which I'm going to define in the next 5 minutes, then this algorithm turns out to perform really well, and it beats out some of the existing state-of-the-art. Another thing I want to emphasize is that this algorithm is objectively speaking very simple. So I have hopes that I can take this talk very slowly, and it could be self-contained. Maybe like 90% should be self-contained. But because of that, if you have any questions or if I'm going too fast, you should interrupt me at any time, right? I have hopes that I can finish everything in 15 minutes, but that's maybe too ambitious. But we'll see how it goes. Right. Okay, so let's get to the actual talk. So we're going to look at the problem called min ST cut, which I believe we all have learned about it at some point as an undergrad. But let's just be a little more precise and define it again. So for the min ST cut problems, the input is a graph, which is undirected and unweighted, and you are given two special terminals, S and T, right? The problem really asks you to output an object called min ST cut. And ST cut is really just like a partition of the vertices that split S and T, and you want to minimize the number of edges across the cut. Right? So here in this example, the min ST cut is like this trivial singleton cut that split S and everything else. And the cut values, which is basically the number of edges across the cut, is 2. Right? So throughout this talk, I'm going to use this min cut G to denote the values of the min ST cut. This is not, okay, maybe if I want to be very precise, I should have said min cut ST of G instead of the global min cut. But then throughout this talk, S and T is going to be fixed, so I'm just going to abuse the notions a little bit. Okay, so whenever I talk about the min ST cut, I should also talk about its sister problem, which is a max ST flow. Okay, so here I'm still given the same graph with the same set of terminals. I also define an object called a flow. I guess there are multiple ways to define a flow. You can define it with respect to net flow of each vertex is 0. But specifically for the undirected and unweighted graph, there's another view that is very useful, at least for this work. And that's that you can view it as like a path decomposition perspective. So I'm going to say an ST flow is basically like a collection of edge disjoint ST paths. Right? You have a lot of paths from S to T, and they are edge disjoint. Then that's my flow. And the values of the flow is just the number of paths I have here. So for example, here is a flow of value 1, right? The green edges is just like one path from S to T. I can also have this little bit more complicated flow of value 1. It just takes a lot of routes, goes around. I can also combine them to get a flow of value 2. Right? So the greens and the orange combined, you get 2 edge disjoint paths. So the max flow is really just a flow of the largest values, right? Simple as that. Here in this graph, you can verify that the max flow is 2, just by taking these two combined. Right. And again, I'm going to use max flow G to denote here. Okay. The reason why we always talk about max flow and min cut together is because of this theorem by Ford and Ferguson. We know it as like a max flow min cut theorem that says these two numbers are essentially the same number. Okay, maybe there's something that's worth emphasizing is that usually when we talk about max flow, we usually define it with respect to, let's say, direct graph, because then you can say the flow has to go from C to D, for example. But here in this setting, the graph is undirected. So maybe like another useful way to think of it is like when you have an undirected graph, you can send like a unit of commodity in this edge in either directions, from C to D or from D to C. Or another way, you can just replace every undirected edge with like two edges, one from C to D and one from D to C. It doesn't change anything. Okay. Before I move on to the convolution models, I want to tell you two very simple but cool facts about flow. So the first fact has something to do with an object called the residual graph. So basically, you take a graph G and you take a flow subgraph of it, call it F. And the residual network is just basically you reverse the flow and put the weights 2 on top of it. Something that looks like this. This is my graph G, and the green edges are the flow F. The residual network is really, reverse F, and you put 2 on top of it. So this is like a combination of directed edges and undirected, unweighted edges. So why do I care about this object residual graph? It's just because it captures like how much more capacity do I have in the graph after I send this like 1 unit of green flow in the left, right? I already send 1 unit of commodity from S to A, then I can afford to send 2 more in the backwards directions. And this is like an object that's used in like, let's say the augmenting path algorithms. So this is something that is used very commonly. So the first fact I'm going to tell you is this very simple looking equations that you can have max flow of G to be as the same number as the flow values of F plus the max flow of GF. There are like multiple ways to prove this. You can do it like by algorithmically constructing something, find augmenting paths, and prove the equations in either directions. Maybe something that's worth mentioning about this equation is that I think more recently, the progress in max flow in sequential time algorithms also use this fact very subtly, in the sense that they just compute like the flow F that is, let's say, like 1/log n approximation of the true max flow and do the recursion on GF. Maybe that is what I'm trying to say is that this fact has been used very subtly in different settings as well. Okay. The second fact I want to tell you is a little bit more difficult to explain, so instead I'm going to ask a question. So here, the question is like, if I want to describe to you a flow of value k, right, the k edge disjoint ST paths, the question is like, how many edges do I have to write down to tell you this flow? Right. So the very naive answer is nk. You have k paths, none of them should take more than n edges, so you don't need nk effectively. So can we do anything better than nk? So here's an idea, right? This is the flow of value 2 that I just told you earlier. So if you stare at it for like 5 seconds, you realize that there's a cycle here. It's in like A, B, D, right? So let me just go ahead and, first remove these edges. They're not relevant. But let's just go ahead and let's try to remove the ABD cycle. So what's happening here is that I break some paths, right? I break the green path, I break the orange path. But then if I spend like 10 seconds on this, I will realize that, actually I can just recolor the edges and still get a flow of size 2 still, right? So the bottom line is that, if I see a cycle and just like throw them out and like recolor the edges, I still get a flow of the same value. So maybe I don't really need as many as nk edges to represent the flow of size k. And that intuition turns out to be true. There's like this very cute fact. It has been proved in the 90s. There are many proofs. But this fact basically says that if you have a acyclic ST flow of value k, actually you only need nk edges to write them down, and square root k edges to write them down. You don't really need all nk. Okay, and now you might ask, is this tight yet? Is it optimal yet? Can you do better in this? The answer is actually no. I mean, at least up to the constant factors. And the example here is just you just stitch together a lot of complete bipartites. And you can convince yourself that if you want to send a flow of value, let's say 4 in this graph, you need to actually send the whole thing. You need to just route everything from left to right. And that's the only thing you can do. Am I going too fast, too slow, or this is good? Okay, this is good. All right. Okay. Now let's finally talk about the. We're going to use these back later, but we're going to talk about the communication models first. So the first model is the two-player communications. I guess the communication complexity really kicks off in the 70s by Yao, and the two-player communication is like probably the most simple, the most straightforward models amongst all of those. So you can ask any questions you like really in this model. And I'm going to talk about the graph specifically. So in this setting, you are given an input graph, still the same graph as before. But the catch is that now the edges of the graph are partitioned across two players. So at least we'll have some set of edges, and Bob will have the remaining set of edges. Right. The players will seize their private graph as a whole. They can do anything they want with it with unlimited computation power. And then they can send the message back and forth. Alice can tell Bob something, right? Alice might tell Bob, oh, I have an edge here, I have an edge there, and Bob might tell Alice back, oh, I have an edge like here and there. Or they can send something much more non-trivial than that. But they can communicate back and forth. And the end goal is that they want to compute a joint task on their graph combined. For example, here, you want to compute the min ST cut of Alice's graph plus Bob's graph. And the notion of cost here is the length of the message. You want to minimize the length of the message. You don't care about the local computations. You want the amount of interactions to be as low as possible. Right. Maybe a few reasons you might care about this model. First of all, this is a model with very few restrictions. It really forces you to think about what sort of information to be communicated between the two players. So this, like, in some senses, this is a good test bed for your algorithms, or as like it's a good framework to try to solve a problem in this framework. And more importantly, communication complexity, maybe not specific to the two-player communications. It's like a foundation that give rise to a lot of lower bounds in data structures, like in streaming algorithms or in like distributed computations. A lot of lower bounds reduce to lower bounds in the two-player model, not two-player, the communication model. So the hope is that maybe you can come up with a good algorithms in this model, or you can prove a stronger lower bound that rules out something. So this is like a nice little fun game, this fun framework to think about for any of your favorite problems. Okay, the second model I want to talk about is the cut query. This one is much more recent. It is started by Rubinstein, Tram, and Weinberg in 2018. Really, in this model, the graph is still, again, the same as before. But the catch of this model is that you don't see the graph. The graph is being held by another guy who we call an oracle. And we don't really have the direct access to the graph. But what we can do is that we can ask the oracle, we can give them a set of vertices, and the oracle has to answer you, what is the number of edges that cross the cut? Right. For example, I can ask the oracle, hey, can you give me a cut size if I cut it at P? And then the oracle is going to go look in the graph and answer the number 3, just a single number 3. So you get 3 back, you don't know which 3 edges cross the cut. Another example is like if you cut it at here, I ask Oracle what is the number of edges that cross AS, Oracle give you 4. Right. And at the end, you want to again solve some tasks on this graph that you don't really see, and you want the number of queries to be as small as possible. Like similar to before, you have unlimited computation power. All you care about is the number of queries you make to the Oracle. Okay. The model is clear. Okay, so among these two models, just a few quick words why you might care about this model. The min cut problems in this setting, it tightly relates to this broader class of problem called submodular function minimization. So the hope is that maybe you can prove the lower bound in that model, which I believe is one of the biggest open problems in the TACS community. Okay, so now let me try to put the two models next to one another. So here, one of them is stronger than the other one, or at least up to like polylog factors. Does anyone have any guess on which model is stronger than the other one? So you can actually simulate the cut query algorithms in the two-player communications. And the reason is this. Let's say like you have an algorithms, right? And the algorithms want to like, let's say try to figure out this cut of t of value 3, of the answer should be 3. So here, I claim that like Alice and Bob can like simulate this query just because have each player just like make the same cut. And Alice figures out, oh, I have like only one edge across this cut. Bob figures out, oh, I have 2 edges across this cut. So they just like shout out the number, right? And then at the end, they just like combine. 1 plus 2 is 3. So every cut query, every Q query algorithms can be simulated using, roughly speaking, Q log n bits of communication. The O2 here is highest poly log n, which I don't care much about in this talk. Right, so cut query is not as strong as communication, but in itself, it's not all useless. You can still do a lot of cut queries even you don't know about the graph. So let me give you some examples. So you can figure out if there's an edge between 2 vertices A and B using only 3 queries. And here's how we do it. Right? This is like the graph that we don't really see. This is A and B, and there are some neighborhoods, and there may or may not be an edge between A and B, right? So let's say like the numbers here are like y is the neighbors of A, z is the number of B, and x is like an indicator, is like 0 or 1, right? Is if the edge exists or not. So if I cut it at A, I get x plus y. Right? If I cut it there, if I cut it at B, I get x plus z. And if I cut it at A and B, I get y plus z. So it's like just these 3 queries, I recover the value of x, which tells me if an edge exists or not. Right? It's very simple, very powerful. You can also set something a little bit more stronger than this, right? Like you can even figure out the number of edges between 2 disjoint set of vertices, basically the same calculations. How about trying to figure out an edge between A and B, right? Oh, like this only tells you the number of edges. What if you want to figure out an edge? You want to pinpoint one. So we can do this in, roughly speaking, log n queries. And here's how, right? You just have like these 2 like set of vertices that are disjoint. And let's just try to split B into 2 equal halves. And then you make like 3 queries to find number of edges between like A and B1, and the 3 for A and B2. And if one of these are non-zero, you just like recurse on that side, keep having the space again and again, and then at the end you only need more than like 6 log n queries. So this is very powerful. So at the end of this thing combined, it tells you that you can use the first thing here, apply it on the repair vertices. You can actually recover the whole graph with only n square queries. Or if you use like some modifications of the third thing here, you can learn the graph with like m log n queries, roughly speaking. Right. So the most trivial thing you can do in a cut query setting is to learn the whole graph and do your task offline, and you pay, let's say, like n square queries. So that's the goal we should aim to beat the n squared. Okay. Now you can do something a little bit more non-trivial, that you can do the edge sampling in like log n queries. Basically, they're very similar to before. You just need to, reweight things more carefully and sample it more carefully. But you can do the random edge sampling in log n queries. And once you can do the random edge sampling, it just like opens up so many doors to these sequential algorithms. You can do the contractions, which is basically just the edge sampling. And the work by Rubinstein, Schramm, and Weinberg, the ISW18 here, it computes a cut specifier with n over epsilon squared randomized queries.
Sorry, I don't miss this. Where does this model come from? Like, what was the motivation? Like, I understand the communication model.
Yeah.
So this model seems like.
Yeah. Okay. Maybe let me go back for a few slides. I didn't write it down too carefully, but the motivation behind this is that if you look at the, let's say like the min cut, you want to compute the global min cut in this model, then then the function, like the cut size function, is submodular. Submodular means like you have the diminishing return properties. Then the min cut problems correspond to the submodular function minimization problem. It's like an example, like a combinatorial example of it. And for the SFM problems, the questions basically ask, oh, I have a submodular functions. I can make like the evaluation queries, and then I want to find the minimizer, for example. And that problems, the best lower bound we know is that you need, let's say, n log n queries to figure out that questions. So I guess the overarching goal is that can you prove any lower bound stronger than n using this model? And I think the motivation, that's the motivation behind the RSW algorithms. They were hoping that this could give like an n square lower bound. But then they discovered that, oh, actually, there's an algorithm that doesn't require n square. I hope that answers me. Yeah.
Sorry, I didn't follow the edge sampling point. If I want to sample a uniform random edge between two sets, it's just like the randomized version of what you said.
Yeah.
If I want a uniformly random edge among all edges, what do you do?
Okay, I didn't talk about it more specifically, but what you can do first is that you can figure out the degrees of every vertices.
Yeah.
And then you, first of all, sample the vertex proportional to the degrees.
Yeah. Oh, okay.
And then you do this the thing. Yeah. Yeah. All of these questions are great. Yeah. Okay. Okay. Once you can do a sampling, you can do a lot more things, right? You can do the cut specifier, which I think is one of the like main contributions of the RSW paper. This is like by no means trivial, right? It's like quite amazing you can do this in the cut query setting. And the paper by RSW also give a randomized algorithm for the global min cut, not the ST min cut. And they use like n log n cube queries, if I'm not mistaken. And then the follow-up work 2 years later by Apers et al., they shave up all the polylog factors and get the flat ON.
So for the cut specifier, do they just show that you can like compute the, I guess what the cut specifier people call the strength of an edge?
Yeah, okay. Yeah. They I guess like for the original algorithms by like Hager and Benzer, they do like they're subsampling the edges, right? And that's something a little bit different here because they only can do like uniform sampling of the edges. You cannot subsample every edge with probability P. So it's something.
It's not literally just implementing the Carter.
Yeah, it's not literally like that. You have to do something a little bit more like clever. You need to like guess the S range in a more careful way and do it in this setting. Okay, and another thing is like for the this algorithm can be made deterministic. I shouldn't say made deterministic. There is another new deterministic algorithms by Anand, Shanrak, and Wang that does it into the 5/3, which beats n square. But it's deterministic. Okay. So in this slide, I intentionally leave out the SC cut problems because I want to spend another slide on it. So I'm going to talk about SC cut in like these two models in the same slide, and hopefully it makes sense. So the trivial algorithms in both models takes n square complexity, right? For communication, you just like exchange the whole graph. For the cut query, you just learn the whole graph and do things offline. So the state of the art in for these models use n to the 5/3 complexity. The first one is by RSW, second one is by ASW. It's like these algorithms on their own, they have their pros and cons, so I just put them both. But the latter one is deterministic. So in this work that I do with Danupon and Yonggang is that we improve this complexity ever so slightly from 5/3 to n5 and 11/7. So just to give a comparison, 5/3 is like 1.66, 1.67, and this is like 1.6 and 1.5758, I believe. So this is like a subtle improvement, but given that people don't believe that 5/3 is a correct answer, and the bar has been like static for quite a while, I think this is like a step into the right directions. And I think many people believe that the answer should be n to 1.5 or even n. So this is at least a step into the right direction. Okay, at this point, I should be upfront with you and say that there are like some observations in the community of continuous optimizations. They use some like IPM-based algorithms that can do this job in like into the 1.5 randomized communication. So, but if you like just compare these two, these are like, well, there are some slightly differences. For example, our algorithm is deterministic and it also works in cut queries. These are the features that this algorithm doesn't have, but maybe it's comparable, maybe it's not. I'll leave you to decide that on your own. Okay. Maybe another thing I want to mention is that if you want to look at the support size lower bound, you kind of need like n bits to write down the min SD cut. You also need like n to 1.5 bits to write out the max flow. So it's I don't have any good ideas of like, oh, maybe like the lower bounds for like max flow should translate to lower bound min SD cuts. Some people do believe that the answer is 3/2. Some people do believe that the answer is n. So maybe you can decide that on your own. All right. Okay. For the remaining of the talk, I'll try to touch on the algorithms that we have. And the starting point of algorithm is really these like RSW algorithms that does it in like into the 5/3 cut queries. So this is like a very nice like one-page algorithm. But if you like look at it more carefully, like I spent like many hours on it. I'm sure you can spend much less time than I do. But then you realize that these algorithms can be improved ever so slightly. It can be made, the complexity of these algorithms can be made parameterized by the min cut value of G. Right? You can improve it from n to the 5/3 to n to the 4/3 times min cut of G raised to the power 1/3. So, and this is always at most n to the 5/3. So the question is like, why do I even care about this parameterized improvement, right? Like at the end of the day, if I take min cut of G to be n, then it go back to n to the 5/3. Okay, so why do I care? So the answer is that we have this like very nice pipeline to compute the min SD cut. Let me write. So this is like a two-step framework. I think it's probably best to explain by pictures. So the first step is that going to set an additive approximation parameter delta. Then this is my graph. The first step is to find a flow f that is large enough. By large enough, I mean it's only delta away from the max flow of G. And this is delta additive away from the max flow of G. Then I'm going to go ahead and make the residue graph out of it. And I'm just going to like compute the min cut of this residue graph, and that's my answer. Like here, if you look at the min cut of this residue graph, it's just this like singleton cut as before. So you can verify it offline that this actually gives you actually the min SD cut of the original graph. But the good thing about this framework is that what is the min cut max flow values of GF? It's just delta, right? I just used one of the factors that I told you earlier. And if I set delta to be small, like n to the 0.99, we already have the efficient algorithm to do this step, right? So I just invoke the like improved version of RSW. And if I set delta to be n to the 0.99, I already beat 5/3 in the second step. Right? So my job is reduced to just beat 5/3 in the first step. Okay, and that ends up to be what we do in this paper. We give the algorithms that does the first step in n square over square root delta. So, and if you like balance out the parameters, you get back to 8/5 and 11/7, as I promised you earlier. So for the rest of the talk, I'm going to be just focusing on like these algorithms, like how do we get to this complexity. They are, in spirit, they are the same algorithms, but they are implemented in slightly different ways for the both setting. Okay, let me state the main result more carefully. So this is like an algorithms that you are given two things. First thing is the graph G, and the second thing is the additive approximation parameters. And the end product of the algorithm is just the subgraph H, which is only delta away from the max flow of G. And the complexity is n square over square root delta in both models. Okay, any questions? Okay, let's talk about the actual algorithms finally. So here is an intermediate question I want to propose. And I think it's, again, it's best to describe by picture. So here's the thing. The input graph is G. And what you are given for free is a subgraph H, which is like K away from the max flow of G. And then your goal is really to move some edges from G minus H to H so that at the end, your graph H has gap becomes like K over 2. You have the gap from K to K over 2. Right. So something is slightly weird here. I use the word move edges. What does it mean? So a useful wheel that I want you to think of is this. You have like a graph H that are given to you for free. This is a graph that you are going to maintain over the algorithms. But then for the remaining G minus H, you should think of it as like a pile of edges you can grab from, right? You just don't think of them as a graph. You just think of them as like a pile of edges, and you can pick whatever you want from this pile.
Sure. Just to be clear, H is always induced by a flow, or
It can be that. You can think of it.
not necessarily?
Not necessarily.
Does this not work unless H is a flow?
You can always, okay, let's think about like this algorithm in like a model independent way, right? You don't really care about the model at the moment. You can always take H to be the max flow of H. Like you can throw out all the edges not in the flow.
Return those edges to G,
You-
so that you restored the
You don't,
relationship.
yeah, okay, in that sense, yeah. If you throw out the edges, you move it back to G minus H. In spirit, it shouldn't change anything. But I would say that you can think of it as H is just a flow. It's very useful to think of it that way. Or you can think of it as you start with H and you just want to throw a bunch of H in it. Either way is equivalent to me. Okay. So what do I mean by move edges, right? So here just view edges as like a G minus H as a bunch of edges. And the algorithm is going to work as, I'm going to look at H, then I'm going to make a pass at the pile of edges. And then I'll decide on, one edge that I want to add to H. So maybe like when I make the first pass, I decided, oh, CT is a useful edge. I want to move it to H. So CT goes to H. Right. And then the step I may want to add SB, and then I add this edge, and then at that point, the algorithms might just stop. They say, oh, it's enough. I already meet this goal. Then I stop. Okay. So our algorithms that solve these intermediate questions, they only move n square over square root k edges. So I haven't told you how to go from the intermediate questions to the actual algorithms, but roughly speaking, you can just start from an empty graph edge, which has gap like max flow of G, and then you can just like halve the gap every time, and you pay n square over square root k at every step, and at the end you reach the gap delta, and the cost of your algorithm is n square over square root delta edges. Basically, you just reduce the gap geometrically until you reach delta, and the complexity just sums up geometrically. But that's not the fun part of the algorithm, so I'm just gonna skip that. Okay. So these algorithms, if I have to define it in one word, in one sentence, I would say it's just like a greedy-ish witness elimination algorithms. It can be explained very simply. Let's try to be a little more formally about like what it means by all of this. So the algorithms will go like this. I'm going to call this guy on the right, I'm going to call it delta, just for simplicity.
Wait, sorry. In this previous factor, you're using this n root k number of edges for the k value flow, or
Sorry, can you repeat the question again?
the fact about the number of edges that you're moving?
Yeah, I'll use that fact eventually.
Okay.
Yeah. Maybe you already see how to do it. Okay. Okay, so here, I'm going to name this guy delta. And the algorithm is going to be, okay, I'm going to define an object called the witness of a graph. What does a witness mean? Witness is basically like a certificate that the max flow is smaller than delta. Right? I haven't told you yet what the witnesses are, but let's just assume that I have a notion of witness that satisfies this invariant. So you can think of witness as like a certificate that my graph has small max flow. Right? And then the algorithm is pretty simple. It's just like these two lines. I'm going to make a pass add Gmass edge. I'm going to make a pass at my pile of edges. And then I'm going to add an edge that decreases the number of witnesses by like a non-trivial fraction. All right. And then I'm going to repeat again and again and again until all of my witnesses no longer exist. And once I do that, I just output the final edge. Just like a simple 3 lines algorithm. So here, if you believe that this witness has a probability of the invariant, then you can probably believe that this algorithm is correct, right? Because at the end, my graph no longer has any witness, which just means that max flow is already more than delta. Still with me so far? Okay, so, but this should be like a correct algorithm, but there's still a lot for me to convince you that this is the right algorithms. So mainly speaking, I need to tell you like what is the proper definition of the witness, and how do you even like eliminate the witness, right? How do you pick the proper HE, and how do you know that the witness no longer exists once you add CE? Right. And more critically, I should care about the number of rounds of these algorithms, right? If I want the number of witnesses to reach 0 quickly, then I should set gamma to be as high as possible. But then if it's too high, then E might not exist at all. So I need to strike a right balance between those two things. Okay, and to be a little more model specific, I should be able to do this in communications and kite queries. Right? And actually, you can do you can do the communications just by seeing this description. You can do it in the communication models already. Simply because, okay, there's another solved properties here that I call it like enumerability, which just like as a sanity check, the witness should only be defined with respect to the graph edge. If you see that, you should be able to list out all the witness of edge. But you don't need to care about this one. Okay, as I was saying, you can do these algorithms in the communication setting already, just because you want to find an HE from the second step that satisfies this inequality. So what you do is really like if the graph from Alice and Bob looks like this, and then the player can just maintain the graph edge on the whiteboard somewhere. Like put it, like we can always like exchange some edges, you just write it down on a whiteboard. And then what Alice can do is she can just, first of all, delete all of the edges already in edge. And then she can go over all of her edges one by one. She can test if this like purple edge makes that inequality true. And then if not, she just try the next one. And then if not, try the next one. And Bob can also do the same. He can just try his edge and try his edge. He just try to add these edges like one by one and see if the inequality is met. So let's say Bob figure out that, the inequality is met if I am to add this purple HE. So what Bob's going to do is just, I'm going to shout out E, right? And add E to the graph. And I just move on to the next iteration. That's it. Right. Okay, so really the communication is not really an issue here if you are convinced that this is a right algorithm. Right? The player can just locally test every edge and shout out the right answer. Okay. So the more critical things to cover is the definition of witnesses and number of rounds. So basically, the witness here that I want to the notion that I want to come up with must have this property of flow invariant. So just to reiterate, the flow invariant is that H has a witness if and only if max flow of H is at most delta. Does anyone have any great candidates for the notion of witness? Yeah, exactly. So you just replace max flow with min cut. And as Elise was saying, just use the cut, right? So this is right. This is a perfectly valid witness. It satisfies all the things. It makes algorithm go through. But the catch is that, first of all, it's a little bit difficult to argue the progress if you use this cut. That might not be clear, but so the graph looks like this. The cut looks like this. This is just like a direct translation of the invariance. So I want to say that the actual witness, notion of witness that we use, we add this notion of a container to the cut. And a container basically means that, let's say delta is 4. The container is really just like a pre-allocation of 4 edges that I let it cross this cut. Right? So what it means is that more precisely, a container is just a set Y of pair of edges from S to T, and this set should have size 4 and contain the edges that already cross the cut. Okay. So in this example, the container is again set of like 4 pair of vertices across the cut, and in this graph, these 2 red edges already cross the cut, so I have to include it. And then I have rooms for 2 more, so I might just pick like these 2, like for example. So you should think of this witness as like my guess that in the actual graph, this is a small cut, and then this is the edge set, or the container of the edge sets of the graph. Right. And you do the same thing. You can also get this witness. This is also witness. This is also witness. You can cut it at different places. You can use the containers at to construct any set of edges that at the end you mix up to delta. So as a sanity check, just want to see how many numbers of witnesses a graph can have. If you have a graph G, then is it like polynomial, exponential, doubly exponential?
Should be at least around n choose delta.
Yeah, you're right. So here, okay, let me just like bound it very roughly. So this is like, you can have like 2 to the n cuts, right? And then here you can have like n choose delta, n squared choose delta, for example. But at the end, it's just like exponential in n. Maybe like it's n to the n. Okay, good. It's gonna come back later, this way. Okay. Okay, so now I'm gonna tell you how do you actually kill a witness. What it means by killing is that, remember, we have this step where we want to like add an edge that remove as many witnesses as we can. So this like notion of killing just captures that. So essentially, you want to be able to identify like what are the criteria that if you add an edge to the graph, then the witness no longer exists. Right. So let's take a look at some examples, and I hope it will clear things up. So you have this witness. So let's try to add this edge BE. Right. So after I add this BE, then the cut is still a cut of size 2. Right. And then the container is still a valid container. It still contains all the red edges, the solid red edges. So really, if I add an edge that belongs to the same side of the cut, it doesn't change anything. My witness is still there. Right, so this is live. On the other hand, what if I add an edge like AD here? Now the edge cross the cut. I should be a little more careful. But the edge cross the cut, I already guessed that AD belongs to the cut. Right, so this is like a perfectly valid witness. So it's still alive. So if anything, if I add AD to the graph, then this AD becomes a solid red edge. It just means that, you know, now this graph has like 3 edges across the cut, and I only allow 1 more to cross the cut. Now let's see another extreme example. If I add AT to the graph, what's happening? It does cross the cut, right? But at the same time, it's not one of the edges that I guess belongs to the cut. So this edge is gone. This witness is gone. So you can write out these conditions very succinctly, that it only happens when the edge crosses the cut, but does not belong to the container. Right. Okay. Is it still clear at this point? I hope it is. Okay, so let's, now I already defined like witness. I already tell you how to kill a witness. Then let's just look at the number of rounds. So as we were saying, the number of rounds depends on 2 things, which is the number of starting witnesses and the rates of decay here. So you start with like exponentially many number of witnesses, and then decay the rates of 1 minus gamma. So at the end, you only need n over gamma rounds. So again, I want to set gamma to be like as high as possible because I want the algorithm to terminate fast. But then if it's too low. If it's too high, then E may not exist after all. So I need to put a right balance into that. And as a main technical lemma of our paper, we show that if you set gamma to be in the order of square root k over n, then this edge E always exists, and the algorithms will just go through. Right? And if you plug this gamma back in, you get like n square over square root k, as you have seen before. Okay. How much time do you have? Maybe like 5 minutes. Okay. So let me run through the proof of this record and wrap up. The proof is only one slide, actually. So let's just expand it more formally. I already have a graph edge that's going to be for free, and the max flow of edge is like f minus k, and I want to show that there exists an edge. This is an existence statement that once I add e to the graph, then the witness drops by a factor of square root k over n. Okay, here's a proof. So let's say we have this magical set of edges that once I add to the graph, then once I add to edge, then it becomes a full max flow. Like the max flow of edge plus q is just max flow of g. So this magical set q, it must exist. The reason is that I can always take q to be g minus h, right? And then if we plug it back in, it becomes just max flow of g. Right, so the most naive thing I can do is to use q to be like g minus h. So the path decomposition view is that once I add q to h, then I should have f h disjoint st path graph. So here's my mini claim. My mini claim is that if I look at any arbitrary witness, then it is q by at least k over 2 edges among q. Okay, let's take an example. This is a witness, right? A witness is just like a cut and a bunch of red edges. Some of them are solid, some of them are the dash edge, which is the guess. But the number of these red edges are f minus k over 2. Right. Does anyone see immediately how the proof goes? Maybe one more thing will help. Let's say I try to add. Let's see where these f h disjoint paths occur in h minus q, right? H plus q. So it's basically f, these blue paths are f blue paths from s to t. So let's just zoom into these blue edges, the thick blue edges across the cut. So how many of them do I have? I must have at least f of them, right? Because there are f h disjoint st paths, and each of these paths must cross the cut at least once. So the conclusion is that the number of blue but not red edges are at least k over 2. And these are for example, these edge on the bottom thick blue edge, these are precisely the definitions we talk about. These edges, all of these edges kill sty, kill the witness. Right? This is the edge that crossed the cut but does not belong to the container. Okay. So at this point, I roughly proved the mini claim one. And then if you just take an average edge in the set Q, it just kills this fraction of the witness. And I'm going to finish by, we can actually show that there exists the set Q that is much smaller than n squared. And the size of Q can be at most n squared root k. You might be able to guess how this n squared root k comes from. It actually comes from one of the facts that I told you earlier. You can just look at the max flow of the residue graph induced by H, for example. Okay, but let's not go over that. So if you plug in size of Q to be at most n squared root k back into these equations, you recover the main claim. Right. Okay. How to reason communication? You just locally test every edge, and I'm going to say quickly that in the cut query setting, things are a lot more murky because you don't really know the edges. So you need to in some sense, you need to figure out if there's an edge between the two vertices at the same time as trying to identify such edge E. So this is non-trivial by any means. So what we end up doing is we try to reduce it to another problems. So we just give a constructive proof of the same main lemma that can be implemented in the query setting. Okay. This is like a fun problem to think about if you are into queries, but let's just skip that. Okay. Just as a summary, I just want to mention like a few open problems. Maybe I just mention one, which is like the last one here. So in this work, the key features that we use is that we use this like greedy witness elimination argument. And really the reason why we can get like a better complexity is that this optimal support size is small, right? You can improve from nk to n squared root k. And we just exploit that fact again and again and again. So we're just wondering if like the same ideas can be applied to different questions in, let's say, convolution complexity. I have some like works with you here, which does this thing for general matching. It does not improve on any existing state-of-the-art complexity, but it just simplifies a lot of things. And maybe there are different problems you can try to apply this framework on. Maybe like offhand min cuts is something I'm thinking about because you have like a succinct representation of the answer in the form of the Gomori-Yu tree. But maybe it applies, maybe it does not. Who knows? Okay. Maybe that's all I want to say. I'm just gonna wrap up just by like putting these slides up here, which is the whole pipeline of our. Okay. And I'll be happy to take any questions if there.
Are there any questions? So there are no deterministic no algorithm for 1.5?
There is none at the moment, no.
Which paper was the randomized 1.5?
I think it's actually was just up on arXiv yesterday. I can send it to you later, but it's by one of my co-authors, Yonggang. Yeah, I'll send it to you later. But if you look at arXiv that posted on October 7, it should be up there too.
Is it a interior point? Is it continuous?
Yeah, exactly. I think like from what I've been told, is like people have already observed that in 1.5 can be done for quite a while, but I think so no one has written it down explicitly up until yesterday, I think.